Imagine a car that delivers perfect all-wheel drive, without connecting its wheels at all. No drive shaft, no mechanical link, nothing tying the front and rear together. For over a century, the industry has believed one thing. If you want to power multiple wheels, you need a physical connection. A drive shaft isn't optional. It's fundamental. But what if that assumption was never actually true? What if it was just a workaround, built for a mechanical world that no longer exists? Because today, companies like BYD are replacing mechanical synchronization with software. And once you understand how it works, the entire idea of a drivetrain starts to fall apart. For most of automotive history, all-wheel drive has been defined by one simple idea. Power must be physically distributed. If one engine generates torque, that torque has to be mechanically split, redirected, and delivered to each wheel that needs it. And that is where the drive shaft comes in. In a traditional system, power begins in a single source, the engine. From there, it travels through a transmission, into a transfer case, then through a drive shaft that sends rotational energy to another axle. Finally, differentials split that torque between left and right wheels. It is a chain of components, a continuous mechanical pathway. And every part of that chain exists for one reason, because power cannot exist in two places at once. This is the core assumption the entire industry was built on, not just in combustion vehicles, but in the very logic of drivetrain engineering. Even when all-wheel drive systems became more advanced, with electronically controlled couplings, torque vectoring differentials, and adaptive systems, the underlying principle never changed. Power still had to move through the car, physically, and that constraint shaped everything: vehicle architecture, chassis layout, weight distribution, even interior design. A central tunnel runs through the cabin, not because designers want it there, but because the drive shaft demands it. Suspension geometry is adjusted, not for ideal performance, but to accommodate mechanical linkage. Entire platforms are engineered around a single spinning component. This is what makes the drive shaft so powerful, not because it is complex, but because it is unavoidable, or at least, it used to be, because this entire system was designed around a very specific limitation. There was only one engine, one source of power, one point of control, and everything else had to adapt around it. But electric vehicles quietly remove that limitation. They don't just replace the engine, they decentralize it. Instead of one large power source, an EV can have multiple motors, each one capable of generating torque independently, each one controlled digitally, each one reacting in real time, and suddenly, the assumption begins to crack. Because if power can be generated at multiple points, why move it at all? Why build a system designed to distribute energy, when you can simply create it exactly where it's needed? This is where the industry finds itself today. Caught between two paradigms, a mechanical world where synchronization requires metal, and a digital world where synchronization is just computation. And the uncomfortable question is no longer theoretical. It's practical. If you no longer need to physically connect the wheels, then what exactly is the drive shaft still doing there? To understand why the drive shaft may no longer make sense, we need to look at it from an engineering perspective, not as a tradition, but as a system governed by physics. The physics limitation. At its core, a drive shaft is a rotating mass. It spins, constantly, at high speed. In many vehicles, this shaft rotates at several thousand revolutions per minute, directly linked to drivetrain speed. And that creates a fundamental problem: rotational inertia. Every time the vehicle accelerates, The driveshaft must accelerate too. Not just the wheels, not just the car, but the shaft itself. And that requires energy. Energy that does not move the vehicle forward. Energy that is effectively overhead. Now combine that with friction. The driveshaft is supported by bearings, connected by joints, stabilized across its length. Each of these introduces resistance, small losses, but persistent. And in engineering, small losses that happen continuously become large inefficiencies over time. Then there's vibration. A long spinning shaft must remain perfectly balanced. Any misalignment, even microscopic, creates oscillations, which leads to energy loss noise, long-term wear. So engineers add dampers, supports, reinforcements, which adds more weight, more complexity, more constraints. But perhaps the most overlooked limitation is response time. A mechanical system cannot react instantly. Torque must physically travel through components, engine to transmission, to driveshaft, to differential to wheels. Each step introduces delay, not seconds, but measurable latency. And in modern vehicles, especially electric ones, that delay matters. Because electric systems operate at a completely different scale. They don't think in milliseconds, they operate in microseconds. And that gap is where the mechanical world starts to fall apart. The legacy solution. To solve these limitations, engineers didn't remove the driveshaft. They optimized it. They introduced lighter materials, better balancing, more advanced joints, electronically controlled couplings. All-wheel drive systems became smarter, more adaptive, more efficient. But they were still built around the same idea. Power must be transferred. Even modern AWD systems, with torque vectoring and intelligent distribution, still rely on mechanical pathways. They can adjust how torque is split, but they cannot escape the need to physically move it. This is the key limitation. No matter how advanced the system becomes, it is still constrained by the architecture it inherits. It's like upgrading the software, but keeping the same hardware bottleneck. And eventually, optimization hits a ceiling. The real problem. Because the true issue isn't inefficiency, it's dependency. The driveshaft forces the entire system to behave as one. Front and rear axles are no longer independent. They are mechanically linked, bound together by a rigid system, which means you cannot control them independently in real time. You can only adjust within the limits of the linkage, and that limits precision. In a mechanical system, torque distribution is reactive. It responds after slip occurs, after conditions change, after the system detects a problem. But in a digitally controlled system, you don't react. You predict. You adjust instantly, continuously. This is where the mechanical approach begins to break, because the future of vehicle control is not about transferring power efficiently. It's about controlling it precisely. And a system built on physical connections is fundamentally limited in how fast, how accurately, and how flexibly it can respond. Which leads to a critical realization. The driveshaft is not just inefficient. It is incompatible with the level of control modern vehicles are capable of. And once you reach that conclusion, there is only one logical next step. Remove the dependency entirely. The solution to the driveshaft problem was not to redesign it. It was to eliminate the need for it entirely. And that begins with a simple but radical idea. Stop moving power across the car. Start generating it exactly where it's needed. This is the foundation of the modern electric drivetrain. Instead of a single centralized power source, the system is broken into independent modules. Each axle becomes its own power unit. At the center of this architecture is something called an E-axle, a compact system that integrates an electric motor, a reduction gearbox, and a power inverter, all in a single unit. mounted directly at the axle. Energy no longer flows through a long mechanical path. It flows electrically. Battery to inverter to motor to wheels, shorter path. Fewer losses, fewer dependencies. But this is only the beginning, because removing the drive shaft creates a new challenge: synchronization. If the front and rear axles are no longer physically connected, how do you ensure they behave like a single system? How do you maintain traction, stability, and control? In the mechanical world, synchronization was automatic. The drive shaft enforced it. Everything rotated together, whether you wanted it or not. But in this new architecture, synchronization must be created artificially. And this is where software takes over. Instead of relying on a spinning shaft, modern EVs use high-speed control systems to coordinate multiple motors. These systems monitor wheel speed traction, steering input vehicle dynamics, and they adjust torque distribution in real time, at extremely high frequencies. In some advanced systems, control loops can operate at hundreds, even thousands of updates per second, often approaching 1000 Hz. That means the system recalculates torque distribution every millisecond. Compare that to a mechanical system, where torque must physically propagate through components, where response is limited by inertia and friction. This is not just faster, it is fundamentally different, because now the front and rear axles are no longer linked by hardware. They are linked by logic. And logic can do something hardware cannot. It can predict. Instead of waiting for wheel slip, the system can anticipate it. Instead of reacting to instability, it can prevent it. This transforms the entire behavior of the vehicle. Torque is no longer distributed, it is orchestrated. Each motor becomes an independent actor, receiving instructions in real time, adjusting output continuously, working together, without ever being physically connected. And this unlocks a new level of control. For example, during cornering, torque can be adjusted between axles instantly, not after slip occurs, but before it even begins. During acceleration, power delivery can be balanced dynamically, maximizing traction without relying on mechanical constraints, and in low-grip conditions. The system can adapt faster than any mechanical differential ever could. This is not just an improvement, it is a shift in paradigm. Because once synchronization becomes digital, the limitations of mechanical systems disappear. No drive shaft, no central dependency, no forced linkage, just independent systems, coordinated at the speed of computation. This is why companies like BYD are not just building electric cars. They are building software-defined vehicles, vehicles where performance is no longer constrained by hardware layout, but defined by control algorithms. And once you reach this point, the question is no longer, how do we improve the drivetrain? But, do we even need it anymore? At this point, the difference between companies becomes clear. Some are still adapting the old model. Others have already moved on. Traditional automakers like Toyota and Volkswagen continue to evolve from existing platforms. Their systems are refined, reliable, highly engineered, but they are still shaped by mechanical assumptions. Power is something that must be managed, not something that can be freely created and controlled. Even Tesla, arguably the most advanced software-driven automaker, still follows a transitional model. Dual motors, front and rear, a digital layer, built on top of a familiar structure. But companies like BYD approach the problem differently, not as an evolution, but as a reset. Instead of asking how to improve torque distribution, they ask whether distribution is needed at all. And that single question changes everything. Because once power can be generated independently, the idea of transferring it becomes obsolete. This is where the competitive shift begins. For decades, the industry competed on mechanical precision. Better engines, better transmissions, better hardware. Now, the advantage is moving elsewhere, toward software, toward control systems, toward how intelligently a vehicle can manage energy in real time. And in that world, the companies that redefine the architecture will not just compete better, they will be playing a different game entirely. For over a century, the drive shaft was never questioned. It was simply part of the car. Invisible, necessary, fundamental. Entire vehicle architectures were built around it. Entire engineering disciplines refined it. Entire industries depended on it. But now, for the first time, that foundation is starting to crack. Not because it failed, but because the world it was designed for no longer exists. Electric vehicles didn't just replace the engine. They removed the need for centralized power. And once that happens, the logic of moving energy across the car begins to fall apart. What replaces it is not another mechanical system, but something far less visible. Software, control loops running thousands of times per second. Algorithms deciding in real time how a car should behave. Not reacting, but anticipating. And in that world, the most important component in a vehicle is no longer something you can see or touch. It's something you can only design. Because the future of the automobile may not be defined by how power is transferred, but by how intelligently it is controlled.